Hello, Mr. Manohar.
Hello, sir. Good evening, sir.
Good evening. So I was there in Rito's session, and I saw that only you were there. So I don't think anyone else also is going to join. My voice is audible, right?
Yes, sir.
Okay. So shall we start? I think we'll start. The people are probably going to see the recording only. So the thing is, see, I don't use R that much. I myself work in MATLAB and Python, but since the course requires R, we'll do some coding in R itself. Yeah. So the thing I like coding, so I will not show what pre-coded things. I will code, and we'll see if we face some error, and then we'll together figure out how to solve that error. So let's start, and before that, let's see which problem we are going to optimize. So first of all, we will. So this font size is fine, right? Or should I increase it? Are you able to see the code
Okay.
clearly?
Yes, sir. Yeah. Yes, sir.
Okay. So first, what we have done is we have imported the genetic algorithm library. Let's see which function we are going to optimize. So we are going to define a function. So in this function, when we say function and we say, okay, this function will take the input of x, and then we say after it takes the input of x, what value it gives out. It is going to do some operation on x that will be stored inside this curly bracket. So let's do that. So for first choice, we will have x squared plus x into cos of x. This is the function that we are going to optimize. So let's see how this functions looks like. How this function looks like. So we have our input argument. It is not necessary that you need to have same thing. So one thing is to note that this, if you are giving in this particular function line itself, if you are defining the input as x, then there should be x inside. But when you call this function, so how you call this function is fp, and then you give some value here, x or y or anything you can give. So let me just do that itself. We will initialize a array. So we can initialize the array. So it will be a sequence from, let's say, we go from -10 to 10, and delta, the interval that we take, let's say we take it as zero point 0.1. So this is our this thing, our y, which is going to be the input for this fg. After we calculate, we let's store it in capital F. Oh, capital F already is assigned to something, I think. So whenever you get this blue color thing, that means that particular thing is already assigned to some function like a library and function. No? So we cannot use that apparently. Well, let's use F. After calculating the value at every y, we store those values at F, because we have already occupied this FP. So let's see how this plot looks like. To draw the plot, you can either use plot itself, and yeah, so you must be knowing that this run command only runs this code line by line. So to run all of the things together, we'll just Control A, select all, and then run. And then if you see here, the figure is showing. Is the figure clear?
Yes,
So
sir.
yeah, so when we do the maximization, we'll get somewhere here, or if we give our constraints, some nice constraints, then we can get here also. So we'll do one without constraint, one with constraint. Before that, like if I am not very certain how to get the line using this plot function, but what we can do, so let's comment this. Maybe first let me comment all these things. Defining the function. And function. Okay, initialize the input array, or maybe argument. This is the argument for that function. Calculation of the function value. It is nice to have these things, and this one is to plot scatter. But I want to see a curve line, so let me draw a curve. So the way curve works is, first argument in this plot, first argument is your x coordinate and second argument is your y coordinate. But in your curve, first argument is the function. So what is the function here? The function here is fp. First argument is function. Then after that we have what is the range of values you want to put inside this function. So we have from minus 10 to 10, and let's say we want to calculate at 10 values. So before that, let me just delete this plot here. Yeah, so let's say I want to calculate at only 10 values. So what it will do, it will divide the minus 10 to 10 in 10 intervals. So minus 10, minus 8, something like that it will do. Let's see what we get. So see, we got a coarser, very coarse plot, right? So if we want to increase this or make this plot smooth, we will just increase the number of points. So it will increase the number of points from minus 10 to 10. Let me give 100. Control A to select all, and you can also run these codes by a shortcut. Control Enter. Control plus Enter. So this is our new and much more smooth flow. Is it clear till now?
Yes, sir. Yes.
Okay. Now let's try to do some genetic algorithm. First, we will do is without without the constraint. Let's first let's do without the constraint. So okay. So we'll have GA, and the type we are going to use is going to be real value. Sorry. And the fitness. Okay, so for now, let's try to maximize this particular function. So the fitness value we will give equal to the function itself. So if you remember, if you seen the code that sir had written, sir wrote this fp, the function again here, like he wrote f is equal to again all these things, but we can just use this itself. We can just use fp itself here. So I'm just not going to write that. One thing to remember is, here it should be a function which takes some input argument and then gives out some value. So that has to be kept in mind. You cannot give a array. So in this case, what is f? F is an array. If you see here, where we have stored the value of fp when we calculated for each and every y. So we cannot use f here. We have to use a function that, if you see here, which is fp, denoted as fp. Okay. Now let's specify the lower bound. So we have for our question lower bound of 10, and upper bound of, sorry, lower bound of minus 10, upper bound of 10, and then so population size is also one of the. So one nice thing about R is, if you write half of the things, it will just show you the rest what should be there, and then you can just press enter, and then you will get the value. Okay, so for population size, we'll do the iteration. We'll try different population size and different matrices. Sorry, different number of iterations. So for now, let me just give population size of 100, and max iteration. See, again, nicely it has shown me of also 100. And this will run our genetic algorithm, and all the values will be stored here. What we can do is, we can so here I'm not actually going for the monitoring function and all those things. Rito has already shown that nicely. We'll just see the final generation, and we'll see how like what is the full generation and what is the best solution. So let's try to plot. We will plot all the points of the generation. But the points we'll use points as a, as a function, and then we'll give the x coordinates. The x coordinates will be stored in GA at population, and you can get the y coordinate. For this particular case, what we have done, we have given the fitness value as the function value itself. So you can directly use that as your y coordinate, or what you can do, you can calculate the value of y coordinate using our this function by giving the input of GA at population itself. Let's see that. Let's give this color of red, and let's see what is the best solution among them. For best solution, you what you do is, best solution is stored in GA at solutions, and you can get the value by doing this thing. Maybe I should do this. I am not 100% sure what is stored in that. So let's just to calculate the value of this population variables and the best solution using the FP itself. And let's give this the value of green. Okay. So till here we have already seen it's just plotting the curve. Here it is calculating, performing the genetic algorithm, performing algorithm, and what do we have here? Here we are just plotting. So let's just see. So here, if you see, this is our final generation. This was our final generation, all the red points, and here is the green scatter plot. I don't think it is clearly visible. So let me just fill it. So to fill a solid circle, you need PHP. I don't know what that is, but it's just some syntax that we'll use. Yeah, so now it should be clear. Is it visible, Mr. Pankaj? Sorry, Mr. Manohar. So this is the green point you see here. That is the best solution, and these were all the solutions in our final population.
Yes, sir. Yeah.
It is clear. Okay. Now let's try to solidify the concept of our mutation, or rather, let's see what happens if we reduce. I don't think there will be much effect when we reduce our population size or max iteration. Maybe there will be an effect. Let's see. Yeah, though not much. Even if we restrict ourselves to only 10 iterations, it is not affecting much. That is probably because we are converging towards the good solution or the best solution before 10 iteration itself. So how we can check that is, you just give plot EA. Select that and control enter. It will run this. So if you see, yeah, so it is within first iteration itself. It is going to the, so this line, green line above with the green dots here, shows the best solution, and this and x-axis it shows the iteration or the generation. So we reached our best solution in the first iteration itself, because we had 100 population size. So what happened was minus 10 to 10, it automatically randomly went to that value and it chose. So let me just give 10 and comment it. Yeah, you see, now we have something. Now we have something. If I reduce my population size, so the initial guess will be, might not necessarily have these things. So let me just reduce my population size to 1. Then let's see what happens. Yeah, see, now we don't get our, okay, we have some warning in GA. Okay, so the GA doesn't work when you have population size less than 10. So yeah, we figured out, we saw something. We have to give 10 at least. Okay, so let's see. Yeah, we have to give 10 at least. So we select everything with Control A, and then Control Enter will run the code. But here we see, here let me see which generation we reach the best solution. So again, we reach the best solution in the first generation itself. So maybe this is not the best problem to justify the significance of population size and population max iteration. But what we can do is, we can certainly use this problem to, justify the use of let me comment this. I don't want to see this. The use of mutation. So if you can recall and tell me, Mr. Manohar, why did we do the mutation?
It is to have a diversified solution.
Yes. So if because if we did only the crossover and all those things, the solution will be more and more biased toward the best solution, right?
Yeah.
Yeah. So let's try to do that if we can actually do that here. So there's a variable called p mutation. Yeah, p mutation. That is the probability of mutation. So at by default, if you see here in the console, by default, the value of probability of mutation is zero point 0.1. Now let's make it as 0 and see what happens. So what I think you should see is you will not see all these red dots here and there. You will see much more concentrated, or even all the population will be hidden behind this green dot itself. So let's see what we get. Yeah, you see, all the diversity and the randomness is gone. How we can actually show that your all the red dots are behind the green dots is by checking here. So in the console, if you see now, I type GA at population, and what you will see is every member of this population has the same value. And previously, when we didn't had this, let me give it as zero point 0.1, and then we had all these red dots scattered around the domain. In that case, if we see we had all the 100 values are almost different, scattered throughout the domain, with some converging towards the best solution. So I hope it helped, justifying why we should keep a mutation, but also we should not keep the mutation too much. So here we have given mutation of zero point 0.1. Let's say if I give a mutation of zero point 0.8, then you will see that here very much of our points are near the best solution. Best solution around 6.3. So if you see, most of our points are near 6.3, and with some mutations which scatters them here and there to search for other optima. So they are, most of them are around 6.3. But if I give a higher mutation probability, what it is going to do, can you tell me, Mr. Manohar, what was the problem with giving very high mutation probability? Okay, so maybe if you are not able to recall, I will tell. So we gave mutation probability or mutation chance so that we can have some diversity in the population in the new generation. But if we give a very large mutation, then we are, completely destroying the convergence of that solution. So it will be just like random search. After crossover, your solution converged to your best solution. You gave it some mutation, and then it converged to the best solution. You gave it some mutation, and then it went around. Some of them went around to some other places to check for other solutions. But if you give high mutation, then none of them will be converging here. All of them will be going here and there in search of the other solution. So let's see, we can actually do that. So if you see here, you see more red dots are here and there, and very less are actually around this green points, right? So this shows that we should actually give some mutation, but very less mutation probability, so that we have some more number of dots converging towards the solution. Is that clear, Mr. Manohar?
Yes, sir. Yes.
Okay, good. So what else is there that we can see from this problem? Yeah, so I was talking, yeah, the constraint. We can actually go for the constraint optimization. So for now, I am doing for minus 10 to 10. Let's see if we can go and do for, uh, let's say I want this particular thing. So let me do it for 0 to 4. This will be the maxima. Let's try to see if we can actually find this also. For that, you need to modify your fitness function. So I will write a new function, because now I need to write a new function, because to incorporate the effect of the constraints. So it is just function, and it will take the input value of x, and now whatever operation is going to happen on x, we are going to write it inside these curly brackets. So yeah, let me put it here. Calculate the value initially. So fp, so it's going to send the value of x into this function, and it is going to get the value and store it inside fp. My constraint is my x should be greater than 0. I want to give that constraint, and my x should be less than 4. So let's just plot it. So to plot, also Rito also mentioned we should use this function called AB line. If you want to plot a vertical line, you use V equal to. If you want to plot a horizontal line, you have to use H equal to something. So for now, we want to plot a vertical line. We'll use V equal to, what is the value? 0. So this is our vertical line plotted at 0, and another vertical line at equal to 4, means sorry, vertical line for the value of x is equal to 4. Yeah, and that's how we got another line. So this will be my new search domain. So let's see how we actually get this. So when we want our x to be greater than 0, how uh, how can we write it in equality terms? Like how should we write it in constraint terms, Mr. Pankaj? Okay, so that is pretty straightforward only. Let me write it. Probably I don't know actually say that, saying that it's same as actually doing it. So my first constraint is g1 is equal to x. Second constraint is x minus 4. My thing is my g1 should be, okay. So the comment is hashtag here. G1 should be greater than equal to 0, and G2 should be less than equal to 0. Is that clear, Mr. Manohar?
Yes, sir. Yes.
Okay. So what we will do, we are actually going to maximize this function, right? So we have calculated the value of this function at this particular at this particular x, all the x's. What we will do is, whenever our x is actually going outside this domain, that means whenever our g1 is less than equal to 0 and g2 is greater than equal to 0, means in this area we will reduce the value of this function artificially by ourselves, and then we will see, we will actually try to reduce the fitness of these points that are outside, and that's how we modify this function and we get the value. So let's do this. So the output of this function is f, so I'm going to write this. F will be, if else loop is there, our the first thing that if else loop will take is the test, as you can see here also. If else, it takes test, and then if the test is correct, then we have to give some value. If it is not correct, then we have to give some other value. Keep in mind, we are going to maximize this. So if my g1 is greater than equal to 0 and my g2 is less than equal to 0, that means my test has passed. So I will give the whatever the actual value of the fitness function, or the value of the function that we get. If that is not the case, then I will give it a very high negative value, sorry, a very high negative value, that is 10 power minus 10 power 4, so that it reduces the chance of that point being selected. This is kind of a backhanded approach we try to apply to to get the solution within our constraints. So let's see if this works. So now that I have modified the function, I am using a new function. I will have to give this particular function f. So to avoid confusion, let me comment this one. I'll give this particular function f inside this. So you can see, actually, if I run just this thing, you'll see that my f is now a function. So I can give this thing inside the argument. Let's see what we get. If you see, my most of my points are inside this, because I had reduce the fitness value of all these other points. So I am getting the solution, the best solution inside my domain. So to make it more clear, let me again draw the AB line, vertical line. So we have to draw a vertical line at 0. And let's give the color to that line as red. And we have to draw a line at 4. Yeah. So our best solution is inside this. We can actually even reduce this particular value to even higher value so that we don't get even more of these points. So let me just do that. I'm giving 10 power minus 10, 10 power 10 here, minus of 10 power 1. Yeah, 10 power 10. So more of my points are inside this. And the best solution is opting. So is that clear, Mr. Pankaj, how we apply constraint? If you have any doubt, then we can rectify them now.
Yes, sir. Yes, sir.
It
It's
is
clear.
okay. Yes. So now that we have seen these concepts in a single variable function, let's go to the multivariable function. Before that, let me just comment here for constraint of genetic algorithm or optimization. Okay, and you can even remove this to avoid any confusion. This is for constraint optimization. And for unconstrained optimization, you can actually, you don't need to write many things. We just have to comment and uncomment something. So we can just do f is equal to fp, so that we don't have to change the fitness value here. Yeah. Okay. And we'll just comment this. I'll be sharing these codes into the in this week's content. So that's why I'm actually trying to put nice comments so that you are able to understand this. Okay. So now let's go to the question 2. So using this plus button on the side here, you can generate a new R script. That should be pretty straightforward. Let's save it as question 2.r. Okay. So this time we will be solving a multivariable multivariable question, and it will be nice. It is the one of the problem that sir showed in the class. One of the very hard looking kind of plots. You will see that. Okay, so let's see. First things first, we have to import our library of genetic algorithm. And now let's see which function actually we are going to optimize. So again, all these things same function. This function is going to take two arguments, x1 and x2, and then it is going to do some operation on that. That particular value is going to be returned. So we are going to write that 20 plus x1 square plus x2 square minus 10 into we start the bracket cos of 2 into pi into, so here if you see pi, it already stores the value of pi inside that pi. So if you just write pi in the console and press enter, it is going to show you the value of that pi. So we can just write pi here in instead of importing like we do it in Python. We can just directly write it here in Python. If you want to get the pi, then you have to import math, and then math.py and all those things are there. So you don't need to do that. This R, actually it's I feel personally, I've used both MATLAB and Python. It's a combination of both the things. It's slower than both, but it is a combination of Python and MATLAB. So this is the function that we are going to optimize. But how this function looks like, for that we need to plot this. So what we'll do, we'll assign some value for the arguments that we are going to give into this function, and then we'll plot it. we'll plot a 3D plot and we'll see how this plot looks like. Okay. So we have x1, x2, and then we can give them value -5 to 5. So this will be our search domain. And for plotting, so that we don't get a very coarse plot, I will give the delta for the plot as zero point 0.1. And we will store the value again for this function. Let's store it in fval this time and give it as. So here's the thing. So okay, let us see that error first, and then I will tell you why we cannot use that particular thing directly. So according to our previous question, that is question one, if we just give the function f is equal to fval is equal to fp of y, it will give us the value of the function at every y. But here if I give fp at x1 and x2, it gave me an error initially. Let's see if I get the same error. Oh, okay. So I don't get the same error. So apparently we can use this. So let's see what does the plot looks like here. So we'll use a perspective 3D that again it has shown us nicely, and then let's plot it x1, x2, and our function fval, and we have to give theta and phi, that is the zenith and azimuth that of the plot that we want to see. So let's do that. Let's see. Okay, yeah. So now it is showing me that particular error. Yeah. So for that, yeah. So this was the error that I was talking about. So we will get the value, but to plot it into this particular perspective 3D, we need a mesh grid kind of value. So to get that, we cannot use this f directly. We cannot put x1 and x2. We have to use a function called outer that will take the value of x1 and x2 and create a mesh grid around that x1 and x2 and calculate the value of our function at each and every point. So fp. Now it should be good to go. Let's see if we get. Yeah. So if you see, now we have gotten. So this was the function probably sir showed. Mm, to exactly see what sir showed, let me just give another color palette so you can be you can get a familiar feeling. Color palette, let's say from blue to green colors. Yeah. So this was the function, that one of the functions that sir showed in the example, right? Here our this conventional optimization approach is going to fail very badly. So for that we need to use genetic algorithm here. So we are going to do the optimization for this particular function. So do you understand, Mr. Pankaj, why did we use outer here?
Yes, sir. Yes, sir. To create the mesh
Yeah.
for plotting with 3D,
Yes.
3D perspective. Huh.
Yes. So let me write it here also. We cannot use this because we need a mesh for plotting 3D. Okay. So this is just the part. So, but the solution that we are going to get, actually, it is going to be difficult to see the solution in this particular thing. So let me just comment this and write a contour, plot a contour, so that we can see much more clearly what is our solution. Okay, x1, x2, and for contour also we need this approach, the mesh grid approach. So we'll use the same fn. And here is the contour. So contour values are also showing 20, 10, 30, 40. So this one of lot of optimas are there, and our minimum optima will be somewhere probably around this 10 contours inside these. So we'll try to identify if we have. So you can actually draw more contours or less contours by giving this n levels, that is the level of number of contours. So I don't know what is the default value, but let's say if I want to plot only 10 contours, then it is going to, okay, probably it was only already plotting. Let's say I want to plot 100 contours. Maybe I should remove this and see what is. Yeah. So it was taking time because it was taking time because I had given so many contours. So that's why it is showing so fine. We cannot even make it out. Let me just stick to 10 only then. Yeah. So 10 contours is fine. Now let's try to write a code for the genetic algorithm. Okay. So here actually in this particular case, we need to make a new function that will be assigned to the fitness function, because one problem with genetic algorithm or any other optimization algorithm is that when you give, so the function that you are going to optimize can have n number of input variables. So these functions that you are going to put, the algorithm doesn't know how many inputs you have. So what it does is it says that you do one thing: you give me an array in which all the values of your arguments will be stored. So instead of giving x1 x2, it says you give me an x and you give it inside two elements, and I will and you in this function itself you specify where you are going to use the first element and where you are going to use the second element. So it will be easier for the optimization algorithm. So that's why we have to make a new fitness value or the function value, so that it will be easier for the algorithm to understand. Otherwise, in this function could have one argument or it could have 10 argument. The algorithm will not know, no, because x1, x2, x3, xn. So we have to make it easier for the computer to understand. So only one argument we are going to give, but this argument is an array. So it is going to have lot of values inside it, and we are going to use them. Let me just copy this from here to here. Function, and instead of x1, let me write the first element of x. Instead of x2, let me write the second element of x. And same thing here. Okay, so this is my function, and since the output is f, let me give here f1. Okay. So if we are doing this, then actually we are looking for the maximum, right, Mr. Manohar?
Yes, sir.
So if I want to get the minimum, what should I do then?
We should use negative.
Yes, thank you. So we will use minus of f1. So this will be our fitness function. Okay. Now let's see the genetic algorithm. So we have our GA, that is genetic algorithm. The genetic algorithm results will be stored in this variable. You can actually give it any number. Let me give this so that you remember that we can give any variable this particular thing. What is the type we are going to use? We are going to use real value, and fitness. We have made a new function for that. Okay, now here's the another part where you have to specify this particular genetic algorithm that you are using two variables. When you give when you give the limits, so if you remember our question number one, we gave lower limit of -10, upper limit of 10. So only one variable was there. That's why we had only one lower limit and one upper limit. But we have here now two variables, and these variables can have different ranges in which they will vary. So we have to give two values for their lower thing and two values for the upper. This C here, if you see, is just so that it creates a array, it creates a column vector or a row vector. with two values. So just let me show this here. If you have x is equal to c, then you will get an array with 1 2 3 3 4 5 values. So this is what you will get. That's why we give it here. Otherwise, if we just give brackets, then it's not going to work out. Probably. Let's see whether it works out or not. Yeah, so it's not going to work out. So we give a C, and inside the bracket we give these things so that it knows we want to create an array. Okay, now upper limit is 5 to 5 for both the things. And what else we need to specify? Population size is there. Let's give population size is 100 and max iteration. Iteration also let's give 100. Let's see what do we get. Before that, let me also plot all these things. Yeah, so let me plot also points we want to see where the solution is, where our solution is going. So it will be it is too much to write. Let me just put it as SD. Yeah, it will be inside SD. We will have our population, and population also will have two values, x1 and x2. So this one we will show all the, like the first argument of the populations, and this one is going to show me second argument of the population. I don't I Yeah, I have written the spelling wrong of population. Okay, I think this is fine. And let's again give it a solid circle, that is pch is equal to 20, and color let's give as red. Let's see if it runs. Fortunately it has run, and you see all your population is going to this particular value for some reason. So let's see what we have in our population. Let's inspect the population. Okay, so we have in our population, first value is almost 0 and second value is 5 for some reason. Okay, that's something I did not expect. Let me see what is going on here. Okay, so this is not supposed to happen. Maybe we'll see. We'll see what is going on. Let me check. But we got the right answer. Yeah, we got the right answer. Let me increase the population size and then see. Again, we are facing the same issue. Some kind of problem is there. Okay, so we we have actually we have actually the things correctly, but for some reason, so if you see here, we have the things correctly only, but for some reason we are not seeing the values clearly here. So maybe some issue with my coding. I don't know. I didn't use this R very often. But you see this point, right? That we have gotten a much closer solution to our optima. Yeah. So that is there. Okay. So that's fine, right? So we have gotten some value. I don't know, some issue with the plotting. I think I will figure it out after this session. What is going on here? Or maybe let me check it's now itself. Okay, let's plot the solution then. The solution will have the best solution, right? So let's plot that and let's see. 0 5. It shows me that my 0 5 is the correct thing. I don't think that is the case. Let me see what is going on in this thing. Okay. How do we how we are plotting in R? So if you see any mistake here, Mr. Manohar, then you can tell me also. We'll see what is going on here. This seems fine to me. Yep, this seems fine. Let me do comment this and let's see what is the summary of this GA. Oh, so it is. I have not stored it in terms of GA. I have stored it in terms of in the variable name SD. So let's see. X1 and X2 are giving 0 and 5. So then definitely there is some issue with our the question that I have written, the optimum that I have written. So let me check again the question. So 20 plus x1 square plus x2 square minus 10 into cos of 2 pi x1 plus cos of 2 pi x2 and then the bracket seems to be fine. Oh, okay, okay. Let me just do this. And summary. Okay. Summary. I have a habit of giving GA. Probably it is. I'm facing a lot of error here. Is it not able to get to my thing? Let's run this genetic algorithm for 100 times. Then see. Summary SD is solution is 5 and 5. So it is going for a maximum value. That should not be the case. Okay. Sorry, Mr. Pankaj, I don't know what is going on here. Let's give me some time. I think we are doing the correct thing, but there is some kind of an issue. Okay. Somebody SD. So I figured out the problem with this particular thing. So when we want to actually plot all these things, population, then we have to. It's a matrix actually, and I want to plot all these first column points in my x and second column points in my y. So I have to see. You see this thing. So first column all the rows, so that you signify by point 1, and second column all the rows, that you signify by point like comma 2, comma 1 and comma 2. So that's how you plot that, but there is some kind of an issue. That's why we are not getting these. So it is for some reason going to the boundaries. If you see all the points here, and it is showing that our optima lies there, but that is not the case. Our optima, that is our minima, should lie somewhere here. Okay, so do Mr. Manohar, do you see the problem now? So
What, sir?
yeah, so actually you see what I had done was my lower limit for x2 and my upper limit of x2 I had defined incorrectly. So for x2 I told no we can have different limits for,
Yeah,
yeah. So here if you
it has become 5 to 5.
yeah, so that's why the all the values of x2 are 5, and we are getting only this particular thing. If I give
Yeah,
minus
it
5,
should be -5.
yeah, then we will get some yeah, now we get some points around our global minimum. Okay, so this is one of the errors that that can also happen. So luckily I spotted that this is the error. Yeah, so let's see if I want my optima somewhere here. So let's use this error to solidify our concepts. So let's see if I want our optima somewhere between 2 to 4 for x1 and 2 to 4 for x2 also. Then we'll give the lower limit for x1 2, and for x2 as 2, and limit for sorry, this thing as 4 and 4, upper limit for both as 4 and 4. So yeah, this is our so at 2 we have 20, all the other things will be more, so we get our global optimum. So does this help in understanding how to work with the optimization genetic algorithm, Mr. Pankaj? Oh, sorry, Mr. Manohar. I'm sorry. There
Yes,
was
sir.
yeah. I'm sorry. I'm calling you Mr. Pankaj frequently because there
No,
was
no issue, sir. Hmm. Uh,
yeah.
uh,
Okay. So this is how we want we do genetic algorithm in our R. So if you want to try something, you can tell me. We still have 5 minutes. We can try that. Okay. So
uh,
yeah.
actually, actually, I have to just practice it before,
Oh, okay.
which I didn't yet.
Oh, okay, okay, no problem. Let me just do try one thing. Let me just show you. Maybe here it will be much more clear about how do we go about, like what will be the effect of giving high mutation. There also it was apparent, but let's see. Control A and Control Enter. We okay. We press to run the thing. So we are having here because the mutation probability is less. But if I change P mutation, and if I give it as zero point 0.8, again a higher value, you will see that it will not be stationary here. All the things will be spread around. Yeah, let's see. Yeah, so see, this is kind of a random search. So this is why it is very important to give a
Yes, sir. Yes.
lower mutation.
Mm.
Okay, let's go back to the practical. Yeah. And uh, is that all in this question? Yeah, I think that's all for today's demonstration. So you can try. If you have some doubt, then okay. One more thing. See, these parameters that I'm changing here in this particular GA, if you sometimes perhaps forget, or you are having difficulty, that one what you can do is you can just uh, type GA, capital GA. Oh, sorry. You give this thing SD is equal to GA and then bracket, and then you give the type the variable that you have assigned SD. Then it will show what are all the options or the variables that you can edit in this particular genetic algorithm. See, we have lower limit, upper limit, we had iterations, maximum iterations, then mutation probability, then probability of crossover, then elitism is also there. Then we have where is the fitness function, Then population size is pop size. So all these variables are there. Then type, that we give real valued. So these things you can see which are all the values you want to change and play around with the genetic algorithm. Okay then, thanks for sticking around. So we fixed one problem that we generated. That makes me happy. Yeah. Thank you, Mr. Manohar. Then I'll end the session for today. Then
Okay. Thank you, sir. Thank you.
thank you. Yeah.